So today, what I discuss is topics are we will derive efficiency of Brayton cycle, and also we will write the expression for heat supplied for Brayton cycle, and as well as heat rejection. That is QR represents heat rejection, QS represents heat supplied, efficiency is eta. And this efficiency equation we will be writing in two two types. One is in terms of temperatures, and one more is in terms of enthalpies. Okay. So before that, we need to understand two concepts. One is what is actual cycle here, and one is ideal cycle. In the actual cycle, just to look at the TS diagram. So point 1, 2, 3, 4 to 1, complete 1 to 4 to 1. This is a actual cycle. Look at the PV diagram, or else in the PV diagram also. Point number 1, 1, 2, 2 to 3, 3 to 4, 4 to 1. It is an actual cycle. Sorry, no, it is not actual cycle. It is ideal cycle. 1 to 2, 2 to 3, 3 to 4, 4 to 1. It is an ideal cycle. Then what is actual cycle is there only one point differs between actual and ideal. So during isentropic process, there is not perfect adiabatic process. So it will be very difficult to maintain constant entropy during isentropic compression and as well as during isentropic expansion, that is 3 to 4. So there will be slight increase in the entropy here. Just to observe, my dear students, the ideally point is S2, but actual process is S2 dash. So there is a slight increase in entropy along x-axis. So if I ask you to write what is actual cycle is 1, 2 dash, 3, 4 dash, 1. So this is actual cycle. So keep in mind. So whenever in the question paper or in the numerical, if they ask you to calculate actual cycle, we need to determine temperature 2 dash, temperature at point 2 dash, temperature at point 4 dash. If it is normal ideal cycle, then T1, T2, T3, T4 are sufficient. If you are calculating for actual cycle, you have to calculate one more extra temperatures T2 dash and T4 dash, and sufficient data will be given for calculating these two parameters. Okay, that we'll discuss later how we'll solve miracles and all. Okay, so just to keep in mind what is the difference between actual and ideal cycle. So now what we do is we will write expression for heat supplied. So heat supplied is QS. And dear students, out of four process, which process is heat supplied, or which in which component there is a heat addition or conversion takes place? Anyone say, tell me, 1 to 2 is a heat addition, or 2 to 3, or 3 to 4? Out of 3, in which process there is a conversion?
2 to 3.
2 to 3. So 2 to 3 it is a heat conversion process. Okay. So during 2 to 3 is a heat addition process. First underline this word 2 to 3. And we know the basic equation for heat supplied. What is the basic equation? M Cp delta T. This is a basic equation. Always we write for heat transfer. So now I am writing for 2 to 3. I will write 2 to 3. Write M as it is, Cp as it is. So in the PV diagram, 2 to 3 is heat addition. Here is a 2 to 3 process. This is heat supplied. And as well in the TS diagram, from 2 to 3, here is a heat supplied. And when you are writing temperature difference, always you take highest temperature first, that is T3 minus, and T2 is a heat supplied equation. This is equation number 1. And dear students, now this equation is with respect to ideal or actual. Look at the values what I have taken here. I have taken T3 minus T2. And T3, both T2 and T3 are ideal case or actual case?
Ideal.
Ideal, very good. So same equation, can you write for actual? What will be the equation? Just try to write. Yeah, what
T3
will be the
minus
equation?
T2 dash.
Yes, T3 minus T2 dash will be the equation for actual heat supply. Okay, very good. Next, similarly, what we do is you will write expression for heat rejected. Heat rejected is which process? That is 4 to 1. 4 to 1 is heat rejected. Here 4 to 1 is the fourth process. Okay, here is the heat rejected. So similarly, write equation for M as it is, Cp. Why I'm writing Cp here? Why not Cv? Because it is a constant pressure heat addition and as well as constant pressure heat rejection. In the previous classes we discussed there are one more term will come MCV. When you to take CV, when the process is at constant volume, you need to take CV. But here both heat addition that is supplied and heat rejection both are at constant pressure. So here that is the reason we are taking CP into 4 to 1. We need to take temperatures. So temperature, where is the fourth point? Here is a fourth point and first point is here. So the process starts from 4 to 1. It is going from point 4 to point 1. So temperature T4 is more than T1. So I will write here T4 minus T1. This I will take equation number 2. Okay, dear students, equation 2 is for ideal case or actual side case. Again, my question is this question, equation number 2, Q heat rejected 4 to 1. I have written this equation MCP T4 minus T1. So this equation I have written for ideal case or actual case.
Ideal.
Ideal case. So what will be the equation for actual? What terms will come into the picture here? Whether T4 will change or it will be remain same.
T4 dash.
T4 dash minus
T1.
T1. Okay. So keep in mind that is the equation. Okay. Now, dear students, now one more point. Next point is important. How to take mass flow rate, M value. Always you will be assuming that it is M is 1 kg for the given cycle. But now look at this diagram. This is important. How to calculate, how to take the value of M. This heat supplied is related to second process, that is 2 to 3. Okay. So let us assume that M1 is mass of air. What is mass of air? That is fresh air enters into the compressor is M1. So what will be the mass of air coming outside the compressor? Again M1, because there is no extra mass we have supplied, or there is no, we have not removed any additional or extra mass from the compressor. So M1, M2 both will be same. So I will take it as M1 only. So this M1 mass of air enter into the combustion chamber. So my dear student, let me draw one small sketch here. So M1 enters into the combustion chamber. Assume this is combustion chamber now. This is point 2. Here we are supplying fuel, F. So assume mass of fuel. So once you supplied mass of fuel with high pressure air, that is M1, combustion starts, you will get gases. Okay, just you tell me what will be the mass of gases, whether it is M1 or MF, or mass of gas is equal to M1 plus MF. Which one is right? Mass of gas is equal to, shall I write only MF, or mass of gas is equal to M1, or it is sum of both mass of fluid and mass of air?
M1 plus
Yes, M1 plus MF. Correct, very good. So here, try to understand in the given numerical, he will give mass of air maybe per 3 kg, mass of fuel maybe 2 kg, like that. He may not give mass of gases during 2 to 3 process, that is, or at 0.3. Mass of gas is at 0.3, not at 0.2. At 0.2, whether it is mass of air or mass of gas or mass of fuel at 0.2. 0.2 is mass of air or mass of fuel? Here, mass of air, because it is coming from compressor and enters into the combustion chamber. And on the top side, we are supplying mass of fuel, that is MF. Here we are supplying MF, mass of fuel. Here, same diagram I am representing here, so that you will understand better. So mass of air plus mass of fuel, once a conversion starts, we'll get mass of gases. So remember this equation, mass of gas is equal to mass of air plus mass of fuel. Okay, this is for actual cycles. If it is ideal cycle, then same, everywhere the mass will be remain same, m1, here also m1, m2, because we are assuming it is ideal cycle. So entire mass flow rate inside the cycle is, we'll assume it is 1 kg. Okay, now we'll go to write equation for efficiency. So what is the equation for efficiency? What is the basic equation? Efficiency is equal to output divided by input. What is output? Always work done. Input for the given cycle is heat supplied. Okay, and dear students, one more point you need to understand here. In the combined cycle, maybe Brayton cycle here, what is the net output is work done by the turbine is WT, and work done on the compressor is WC. So this work done, net work done, can also be calculated WT minus WC. Keep in mind, WT minus WC. What is WT? Work done by the turbine minus work done on the compressor. If you subtract these two, you will get net work done by the cycle. For example, the turbine is giving 100 joule of energy. Out of 100 joule, 30 joule energy you are transferring to the transfer to compressor using this shaft. How much you are transferred? 30 joule. If I ask you to what is the net power or net work done by the turbine, what will do? 100 minus 30. That is a 70 joule is a net work done from this cycle. So keep in mind, this is also one formula. And work done by turbine, work done on the compressor, he may give value directly, or you may calculate using some formulas that we'll discuss later how to solve. So work done, what I do is I will not write in terms of this equation. I will write net work done in terms of heat supplied minus heat rejected divided by heat supplied. Why I'm writing this equation is because in the previous classes always we have written work done is in terms of heat supplied minus heat rejected and divided by heat supplied is as it is in the denominator. So 1 minus QR by QS. So this is our basic formula. So substitute the value of QR. What is QR? 4 to 1 process heat rejected M CP QR is T4 minus T1 divided by what is heat supplied? Heat supplied is equation number 1. It is here M CP T3 minus T2. Okay, so this is efficiency of Brayton cycle in terms of temperatures, because both mass get cancelled, CP is also get cancelled. Okay, so only left is 1 minus T4 minus T1 divided by T3 minus T2. So this is an efficiency equation in terms of temperatures. But as we know, all temperatures will not be known or not be given in the numerical. Only T1 will be given. The remaining T3, T2, T4, all we need to calculate. This is what we have done in the previous air standard cycles in the diesel engine. We converted temperatures in terms of volume. Understood? And one more point here in the air standard cycles, all temperatures we have converted in terms of compression ratio. That is, if you remember, we have written like this: T2 by T1 is equal to V1 by V2 to the power of gamma minus 1. V1 by V2 is compression ratio RC. V1 by V2 is compression ratio, and R value will be given in the numerical 15, 16, 20 like that. So in place of T2 by T1, we have substituted RC. But here no question of clearance volume because there is no piston cylinder arrangement. Compressor is different part, turbine is different part, combustion chamber is different component. So here it is not a piston cylinder mechanism. So I cannot write take clearance volume. We cannot write stroke volume here. We cannot write swept volume like that. Understood? So don't write Brayton cycle is in terms of compression ratio. It's not like that because it is not a piston cylinder arrangement. It is completely all each and every process. It is undergoing different components. But in the air standard cycles, diesel cycle, petrol cycle, dual cycle, so all four process was carried out in a single component, that is piston cylinder. So now we will convert all temperatures into known values. Okay, so this is equation number 3 you consider. Consider equation number 3. Next, what we do is, so question arises in our mind, sir, if clearance volume is not available, we cannot take clearance volume, compression ratio also we cannot take here. So what is the known value? The known value is, look at this diagram. Okay, P1 will be known for us. P1 is the pressure of the air at the entry of the compressor, and T1 is also known. We don't know T2, we also don't know T3, and T4 will be known because it is going to atmosphere. We can measure T4 also. So what the industry people, scientists will do is, they will write pressure ratio. One more term will come here, pressure ratio. P2 by P1, this value will be given. P2 value will be given, or P2 by P1 ratio will be given. That is called as pressure ratio. So now what we do is very important step. It is for solving numericals as well. Convert temperatures in terms of pressure ratio. In terms of pressure ratio. In the air standard cycles, what we did, we have converted temperature ratio in terms of volume. In terms of volume we have done. Because we know that clearance volume will be given, stroke volume will be given, or V1 by V2, total volume by clearance volume will be given. That is compression ratio. But here we don't know the values of clearance volume, stroke volume, or compression ratio. Instead of these three, we know pressure ratio, that is P2 by P1 or P3 by P4, like this, P3 by P4. During 1 to 2, we know the pressure ratio, that is P2 by P1, and during 3 to 4 process, that is expansion process, we know the pressure ratio P3 by P4. So we will, hello, please mute yourself. Okay, so now what we do is we will convert these temperatures into pressure ratio. Keep in mind. So I will write an equation on the board how to convert temperatures into pressure ratio. Very important. Remember for solving numericals also. Okay. So what I do is I will write temperatures into pressure. So first I will consider the process 1 to 2. Process 1 to 2 is isentropic compression. What is the expression for isentropic compression? T2 by T1 . Okay, T2 by T1. In the previous, we wrote like this. It will help you. For example, I will write V1 by V2 to the power of gamma minus 1. So I cannot write this equation, but left hand side will remain same, T2 by T1. I will convert V1 by V2 into pressure ratio. Pressure ratio. How to convert V1 by V2 into pressure ratio? Anybody? I cannot write this equation, but for time being, I will write and I will convert. How to convert V1 by V2 into pressure ratio? Anybody? Is there any equation you know which converts the relation between pressure and volume? What is the type of
Ideal
process?
gas.
One to what? Yes, very good. Ideal.
Ideal gas equation.
Ideal gas equation, PV is equal to MRT. This is for at particular point. But what is the name of the process between 1 to 2? What is the name of the process? It is constant pressure or adiabatic process. 1 to 2 is what is the name? 1 to 2. What is the name of 1 to 2 process?
Reversible adiabatic.
Very good. Reversible adiabatic. What is the law for adiabatic process? What is the equation? Adiabatic process. PV to the power of gamma is equal to constant. Understood? Now you write this equation at point 1. So P1 V1 to the power of gamma is equal to constant. Similarly, you write this equation at point 2. P2 V2 to the power of gamma is equal to constant. Now what I do is P1 by P2, I will take the ratio. Okay. So V1 by V2, like this ratio, I will convert. What is C here? C is constant. What is C? The T1. And here it is T2. Okay. So here I will write T1 and here is T2. So using these three conversions, I will convert this volume into pressure. Okay. So in place of V1 by V2, we can substitute the simplification of these two. Please remember this. I told you in the class how to convert volume ratio into pressure ratio or pressure ratio into volume. So directly I will write T2 by T1 is equal to P2 by P1 to the power of gamma minus 1 by gamma. Keep in mind this equation is new equation. This is in terms of temperature ratio and pressure ratio. Okay, this was the equation we remembered in terms of volume. This is in terms of volume. Now in this chapter I cannot use this equation because it is not a piston cylinder arrangement. There is no stroke volume, there is no clearance volume, there is no swept volume. Understood? But instead of swept volume and clearance volume or compression ratio, pressure ratio will be given. So I will be using this equation. Have you got this equation? Using this. Write V1 by V2 in terms of pressure and temperature. Substitute here. Temperature terms you take one side and pressure terms you take one side. You will get this equation. Okay. This is for 1 to 2 process. This is for 1 to 2. Can I write same equation for 3 to 4? Will you please anyone suggest me to write similar kind of equation, similar equation for expansion process? Try Muddy. If it is wrong also, no, don't worry. T2 by T1 we have taken, it is for 1 to 2 process. My question is write for 3 to 4. Similar kind of equation you write for 3 to 4. So between 3 and 4, which temperature is more? 3 to 4 process. Here is 3 to 4. Which temperature is more? T2, T3 or T4? So T3 divided by T4 is equal to, here T2 is there, you have taken P2. Here T3 is there, of course I will take P3. P3. T4 is there, I will take P4 to the power of gamma minus 1 by gamma. Now the question is whether P3 is known value. No, we don't know P3, but we know P2 is equal to P3 because it is constant pressure process. P2 is equal to P3 and as well as P4 is equal to P1. Pressure at point number 4 is at pressure at point number 1. So same equation now I can write in place of P3 I will write P2. In place of P4 I can write P1 to the power of gamma minus 1 by gamma. Okay, what is P2 by P1? P2 by P1, it is called as pressure ratio. My dear students, remember it is a new term, pressure ratio. That pressure ratio will represent with symbol letter RP. Onwards, remember this. RP is pressure ratio. In the previous module, we solved many numericals with RC, that is compression ratio. One was cutoff ratio. Cutoff ratio was rho. Understood? That is V4 by V3 was cutoff ratio. Similarly, here pressure ratio is RP. RP is pressure ratio. So this pressure ratio I will substitute in any one equation, just simple for simplification purpose. So same T2 by T1 is equal to RP to the power of gamma minus 1 by gamma using this equation. And similarly, using this equation, the right hand side is RP, left hand side T3 by T4. Same I can write T3 by T4. Now T2 by T1 is equal to T3 by T4. We have written equation in terms of ratio of pressure, temperatures. But what is the equation for me? Efficiency is equal to 1 minus T4 minus T1 divided by T3 minus T2. I need this equation, but I have written in terms of ratio. And we know already we have solved in previous numericals by doing something mathematical rule, we can write this equation in terms of in this equation. Anybody will help me? Do you remember? We once upon in the previous model 3 we have converted ratio of temperatures into difference of temperatures. Okay, I will give hint how to write it. Please look at the board. First I need T4. T4 minus T1 I need. So first try to write in terms of T4 ratio, T4 by T1. This term I will take on the left hand side and T3 by T2. So simple question, why I am converting this into this equation is because I need difference between T4 and T1 difference between T3 and T2. So T3 and T2 ratio I have taken, T4 and T1 ratio I have taken. Now simple mathematics I will do. I will subtract the -1 on both the side. I will subtract -1 on both the side. Mathematically I can do it. Here I am subtracting -1 on the left hand side, on the right hand side also -1. So doesn't make difference with this equation. So now you take LCM, what will become T4 minus T1 divided by T1. Here what will be the LCM? T2. So T3 minus T2 divided by T2. So now you can write the ratio. Here we will get ratio T4 minus T1 divided by T3 minus T2 is equal to T1 by T2. So you got this equation now. Here is the equation. Here is the equation. So in place of this entire term, entire temperatures, I will substitute as only T1 and T2. So efficiency is equal to efficiency of Brayton cycle is equal to 1 minus T1 by T2. 1 minus T1 by T2 I will write. So what is a T1 by T2? Here is the ratio. Okay. Again, sir, you can ask a question, sir. We don't know T2. Again, we have written expression in terms of T2, but we don't know T2. T2 is the intermediate temperature. Yes, very good. Your doubt is correct. But I am not writing in terms of temperature only. Again, I will write in terms of pressure ratio. I will convert into pressure ratio using this equation. Here I know the ratio, no? I know T2 by T1 in terms of pressure ratio. So same equation, I will write it here. So 1 minus P1 by P2 to the power of gamma minus 1 by gamma. Or else simplify the equation, you will get 1 minus 1 divided by this P1 you take in the denominator because pressure ratio is P2 by P1. P2 by P1 is pressure ratio. So pressure ratio to the power of gamma minus 1 by gamma. So this is an expression for Brayton cycle. So keep in mind RP is pressure ratio. Pressure ratio, that is P2 by P1. Don't think that it is compression ratio and all. Okay. So 1 minus 1 by RP to the power of gamma minus 1 by gamma. It is not into. It is not into. Let me write once again here for Rp to the power of gamma minus 1 by gamma, that is 1 in the numerator. So this is final expression for Brayton cycle. Okay, it will be used for solving numericals. Okay, 10 marks or 12 marks numericals will be there. So what we have written is just I will glance first in the today class. We have written expression for heat supplied. Heat supplied is that is during 2 to 3. Let me remove all this so that okay. Heat supplied is during 2 to 3. We know the basic equation of heat supplied is mCp delta T. So first write as Q. M is mass of working fluid during 2 to 3 process. So during 2 to 3, it is mass of gas and mass of air. So mass write as it is. Later I will substitute. M is into Cp. Why it is Cp? Because 2 to 3 is a constant pressure process. 2 to 3 heat addition is constant pressure process. So Cp. And I given hint already is how should write the temperature difference during 2 to 3. Look at the PV diagram. Here is a 2 and here is a 3. Always you take highest temperature first minus lowest temperature during that process, not entire cycle, only between that process. During 2 to 3 I am writing, so look at only 2 to 3. So T3 is more compared to T2. So T3 minus T2. Similarly, you write heat rejected MCP T4 minus T1. This is equation number 2. And keep in mind, this equation will be used for solving numericals. The mass of gas inside the turbine. Here heat rejected is in turbine only, no? It is come outside. Mass of gas is equal to mass of air plus mass of fuel. And we know the basic equation, efficiency is equal to work done divided by heat supplied. Work done is heat supplied minus heat rejected divided by heat supplied. Simplify the equation and substitute 1 and 2, you will get in terms of temperatures. Dear students, I know only the temperature T1 because T1 is initial condition. T2, T3, T4 are not initial conditions. It is intermediate points, intermediate temperatures. We cannot put our hand or any measuring instruments to measure the temperature. So what we need to do is convert all temperatures into pressures. Okay, not volumes here. We cannot convert into volumes. Okay, so don't waste your time in converting temperatures into volume. That is for air standard cycles. That is for dual cycle, diesel cycle, and Otto cycle. Because we know clearance volume will be given, stroke volume will be given, or compression ratio will be given. So in that case, we use such type of conversions, correlations, equations. But here we cannot. Okay, so now conversion of temperatures to pressure ratio. So process 1 to 2 is a reversible adiabatic compression. So reversible adiabatic is PV to the power of gamma is equal to T1. So use this equation, same equation. Why I have written this equation is for understanding purpose, because this is the equation we have used many times in the previous classes numericals. So use this equation and convert V1 by V2 in terms of pressure. In terms of pressure using this equation. Okay, you simplify this equation, 100% you will get this. On the right hand side, I have shown you the procedure also, how to convert governing equations of pressure, temperature into volume, or volume, temperature into pressure. Okay, you simplify this equation, you will get this. This is for 1 to 2 process. Similarly, you write for 3 to 4, that is expansion. So you will get one more equation. Keep in mind P2 by P1, I will call it as pressure ratio. I will call it as pressure ratio. So that pressure ratio, I will take it as T2 by T1 is equal to T3 by T4. Again, this equation is not what we need. This is we need in terms of differences, but here it is ratios are there. So I need T4 minus T1. So to get into this equation, so what I did is just I have subtracted -1 on both the side to this equation. Okay. So once you subtract, you take LCM, P1 LCM you take and simplify. Once you simplify, you will get this equation. It is exactly similar to what we need. So in place of this right hand side difference in temperatures, you substitute as T1 by T2. What is T1 by T2? T1 by T2 is P1 by P2 to the power of gamma minus 1. It is there, gamma minus 1 by gamma. That you substitute here, and P1 by P2 is not compression ratio. P2 by P1 is yes pressure ratio. Is pressure ratio. So pressure ratio will be given in the numerical. Okay. So this is a equation how you will convert into. So what we do is arrow symbol. So 1 to 2 is reversible adiabatic compression. 2 to 3 is heat supplied. 3 to 4 is expansion process. 4 to 1 is heat rejected. Okay, so this video will be uploaded in the YouTube to practice, and so that it will become easy for solving numericals, because same equations will be used for solving numericals. Whatever the equations we have covered today, same equation will be used in solving the numericals. So the next class we will solve numericals. Any doubts are there? Do you have any doubts? Please ask if you have any doubts.
No, sir.
Okay, thank you. So in the next class we will solve numericals. Okay, so thank you for attending today's class. Take care. Bye bye.